here, for the three-phase rectifier, controlled ones, if we remove this part here of those thyristors, they will be like the previous lab, with the diodes only. And this what we call a normal conduction, means the current comes and depends on the polarity of the diodes, and which one is more positive, which one is more negative, and the current will take that path. Here it's same. Instead of diodes, we follow the same philosophy, but we can control it. We have ability to open and close the path for the current. You remember for the diode, I don't know if you can see the mouse here, the pointer. The diode, we said that between 30, this intersection here, and 90, both diodes will conduct the one connected to phase A, because in this interval, phase A is the most positive, and in the same interval, phase B, is the most negative. So A and B, okay, they take lead among those three voltages here. So A means D1 for the diode, and the B, which is D6. So here we'll be having D1 and D6 conducting here, both of them. Now, same thing, it's T1 and T2 will be conducting in this interval here, but we have ability to delay the conduction. So here, between this point and this point, both thyristors, they are ready to be open and to conduct, and it's for us to decide when to give them the order to open both and give the path for the current to continue circulating. Okay, so each thyristor, let's say, for example, thyristor number 1 would conduct for 120 degree. This is rule number 1, or information number 1. Number 2, let's say pair of thyristors. They conduct for 60 degree. Okay, and if you come here, if you come to this side here, the load, to have a voltage across this load, whatever is it resistive only or inductive or whatever type of load we have, across this load here, we should have 2 of these voltages across it. So to have this condition here, one voltage here and the other on the other side, we should have 2 thyristors conducting at the same time. If we have only one, there's nothing. The other side will be open here, so it's an open path, and the current will not circulate in that circuit here. Okay, so keep in mind, to have V across this load, V out here, a couple of thyristors should conduct. Okay? And if we start, for example, at this point here, that's our reference, for example, starting reference here. Let's say this is a T0. At T0, okay, we said that each thyristor will conduct for 120, which is from here to here. This is the most positive among the 3 of them. So here we have this phase here, which is phase A, and phase A is connected to this upper one here, which is T1. So T1 will be conducting from this side, from T1, which is 30 degree. Let's say for the time being, alpha equals 0, for example, okay? So from 30, scroll up a little bit, from 30 till this point here, that is T1. So from 30 to, should be here, 150, because 30 plus 20, we said each thyristor will conduct for 120 20 degree. So 30 plus 120. This is 150 here degree. Okay, the next one will be from here, from this intersection to this intersection here. That's the most negative here, and this is phase number C, and phase C, which is 2. So from this side, this point, sorry if I don't draw like perfectly, but by hand it's something like that. So from this point, which is 90 degree, plus 120, that should be 210. So here will be 210 degree, and this is for T2, and so on. So if we go up again here, after that, from this intersection to this one, that's the most positive. The most positive, which is B. B will be T3. Keep in mind, the upper ones here, the positive sequences or part of the sequence here, those are connected to the upper thyristors, this side. The most negative to the lower ones. So from here, from this 150, say from here, 150 till this point, so 150 plus 120, that is 270, and that's the case here, as you can see. From this point to this point will be A. So A, that is T4, and this was T3. So T4 will conduct from this point here, which is the one where T2 was stopped, which is 210. So 210. So from here will be, I don't know how we can do that. From this point till here will be T4, and that is for 210, plus 120 will be 330 degree, which is this point here before 360. After that, here, of course, and we'll talk about one sequence only, so we have to stop here at this point. So here, the most positive now, it's a C, but C only this part plus that part here. Sorry, for C will be from here to here, plus this part which is seen from the other side. Okay, so will be from here. We go down again here. That is T5, because it's a C, and C in the upper side, it's connected to 5. That's C here, connected to 5. So we're talking about tyrosine number 5. So it will start from sorry, not from here. So start from here, 270. So 270 plus 120 will be 390. Of course, we don't have 390, so we're going to stop at 360. Let's say here 360. And the other remaining, which are 30. So 30 will be seen here before here, from 0 to 30. So that's T5. Sorry, T5, yes. This is T5 here and here. Okay, so if you add this part, which is 6, sorry, that part here plus 30, this is 90 plus 30 will give us 120, and that's the conduction time for T5. Okay, now the other part, which is from here. Okay, the most negative, we have this part here. That is for B, and B is connected to 6. The last one to talk about now. So from this part here, this point, which is 330, 330 here, this point, plus 1 plus 120. This will give us 5. Okay, let's explain it another way. So will be plus 30, the remaining. So this 360 here. And we need another 90 because here, this T6 conducted here only 30 degree, and we need the 90 to be to continue conducting or the conduction for this T6. So the other 90 will continue from here, from 0 till 90. That's T6. Okay. Now I was explaining how thyristor by thyristor they are conducting. Now, if you understood this, I'm going to summarize everything in one line here. It will be more clear than this, because here I need just to match those segments here with the three-phase system up here. So from say 30 till 150, see here, that is T1. From 90 that is 90 here, till 210. This will be T number 2. Here, T3 is going to conduct from 150 till 270. That is 70 here. Okay. T4 will be from 210, okay, till 330. T5, 4, that is 4, sorry. Okay, let's write it down here. That is T4. T5 will be from, even if it's not equal segments, but the numbers, they explain everything here. Let's say this is 360. This is T5 plus here, that side here, from 0 to 30. That is T5 also. Okay, T6 will be from 330 till 360. That is T6. And the remaining will be from 0 to 90. Now, if you just, if you just calculate this minus this, will give us 120, 120 here, 120 for each one of them. Okay. So from here to here, that's this is 90 plus 30 here will be 120. Here we have only 30 from 330 to 360. That is 30 conduction for T6. The remaining will be from 0 to 90. This is 120. So it's clear that each thyristor conducts for 120 degree. Okay. Now, a couple of thyristors. Okay. If we come here from 0 to let's say we start from 0, yeah, 0 to 90. This will be this part, this one, and this one together. So that was T1, and this is T6. So T1 and T6, they conduct between 30 and 90 degree, and those are 60 degree, okay, for each pair of thyristors. After that, we'll keep T1 on, and we make T6 off, but as I told you, we need all the time 2 phases to be seen across the load. So the other thyristor, the next one to be fired and to be open, which is T number 2. So here, from 90 to 150 would be T1 and T2. Okay, here would be 3 and 2. So you see, each time we keep one open, we close the other one, we close it. Means we eliminate it off, we make it off. We make this one on, we keep it on, and we bring the other one with it. So 3 will be with that one. Okay, now we keep 3, we make a T off, T2 off, and T3 on. Okay, and we open 4. That is 4 here with this 3. Okay, now the rest here will be 4, sorry, will be 4 and 5. So we keep 4 on, and we make 3 off, and we open 5. And so on. So in here, we'll be having 5 and 6, and this is for 30 degree here. Okay, even if the segments, they are not symmetrical here, but in terms of numbers, as I told you, this will be 30. So T, sorry, for Z, this is T5, because 4 was conducting before here for 120. So we should not keep it more. Okay, so we give time for T5 to conduct for 120 degree, and we bring T6 with that one. If we go back here, the other 30, the remaining for 60 degree, that's 60 degree here. So 30 will be 30 degree here, conduction for T5 and 6, and will be also the other side, 6 and 5. So T5 and T6. Okay. Now across the load, I think it's clear. Okay, no need to tell me that it was not clear. And but still, if you have any questions, you can ask me. So this is a load, and this is a let's say plus and minus, for example. Here, 5 and 6 will be conducting from 0 to 30. 5 to go up. 5 and 6. These would be C and B. So here, V, we said 5, so CB. So VCB will be applied across this load. T1 and 6, 1 and 6, so will be A and B. So VAB. This is line to line, okay? After that, 1 and 2, 1 and 2, yeah, 1 and 2 will be A and C, BAC. 2 and 3, so will be B and C, and so on. That is B here, B and C. T3 and 4, 3, 4 will be B and A, so VBA. 4 and 5, so will be C and A, VCA. And 5 and 6, which is that one CB, that is A here. And VCB. And so on, okay? And the sequence will continue like that till we stop our system. Okay? So now, once you see, across that load in which voltage you have, You can, this is line to line, you can convert it by divided by root of 3. You can convert it to phase only if you like. Do you have any questions? Is it clear how it works and when we can fire the thyristors? So one more time here, for example, at t equals 30, this is our starting here. We can fire this thyristor starting from here. Can delay that. Okay, 30, 60 degree. Okay. And here also at that time we can fire. So like 60 degree after, we can be able to fire number 2. Fire means make it on. Send the pulse, okay, to the gate of that thyristor. Okay, so send the pulse to this one. This is fire. So once we are able at this point here, for example, so at 90, starting from 90, we'll be able to fire number 2, not before. Okay, and 150, we can fire now this, and now the alpha will be not variable, of course. The alpha will be one value, and this depends on your V out, the wanted V out. If you remember, maybe in the lecture you have seen that V out cross this load here equals depends if that's 3, and depends if it's line to line, so it will be V line to line peak, the maximum, divided by pi, and times cosine alpha. Okay, or V naught would be 3 root of 3 V phase now, not line to line, and also peak maximum, divided by pi times cosine alpha. So if you see the supply, that supply here, it's all the time fixed. Okay, it's not variable one, so it's fixed one. If it's fixed, it means this value is fixed. It's constant. This is constant, of course, and that's constant. So all this term here will be constant. And the only way to control or make this one variable, this V out, make it up and down, it's by controlling alpha. That's the only way to control this V out. Since this one is all the time constant, this term of this equation here. Okay, now I think in trigonometry you took this, that is the axis of cosine, and this is axis of sine. Now, if theta is smaller, or alpha, let's talk about alpha. If alpha is smaller, if you project that here, this will be, and keeping in mind that cosine alpha is all the time between -1 and 1, not below that, not more than this. Okay, so this will be closer. If we minimize alpha, will be closer to 1. If we maximize alpha, to make it bigger like this, for example, okay, this is alpha. If we project that, we are going towards 0, minimizing cosine alpha. So if we increase alpha, we are minimizing this term here, cosine alpha, and of course, this will be minimized. If we decrease alpha, we'll increase cosine alpha, and we'll be increasing V out. It's a proportional relation between V out and cosine alpha, and inversely proportional between V and alpha, not cosine alpha. So this is how it works, our system here, the controlled three-phase rectifier, full-wave rectifier. Okay, so I explained, thyristor by thyristor and a couple of pair of thyristors together, how they work, and for how long they work. And I think we should be able to simulate that now. If you go back to our exercise, That is our exercise here. We're asking you to use this, it's a three-phase controlled. They call it 6-pulse or three-phase controlled rectifier. Okay. Why 6 pulses? If you come back here, look how many pulses do we have. This is 1 pulse, another one here, here. Okay, let's start from it. This is 1, 2, 3, 4, 5, and 6 here. Okay, this pulse with this pulse, because this is VCB, VCB is same. So I have 6 pulses in 1 sequence. That's a sequence. This is a T, which is 1 over, let's say, 50 hertz, for example. Okay, so during this time, which is 0.02 seconds, during this time, we have 6 pulses will be seen across the load. And those are the top, the maximum of, phase to phase. If you are able to, this is only phase to neutral, this is per phase, that system here, this graph. If you are able to plot VAB, VBC, and VCA, and so on like that, you see that you'll be having the top of these VAB and VAC will be seen 6 times across the load. But that's why they call it 6-pulse controlled three-phase rectifier or converter. So the one we need to simulate is the one here. We have the supply is connected in Y connection. Okay, and this one here, this will be between line to line. This is V line to line. So if you have Y connection, means from between A and B, we have this value. If you need to plot your VA, VB, and VC by itself, you have to convert this one from line to line to phase only. You divide this by root of 3 before you plot your three-phase system, the one you see here. Okay, this is line to line because it's a Y connection, not delta connection. The phase, the frequency is 50 hertz. Your load, it's like this one here, R and L. You have those values given to you. You have to determine now the alpha needed to supply this much of current to the load. This is average. Keep in mind, average. Okay, the average will be seen across the resistor. Okay. So you have to do, you know what to do. There's a relation to find your V out, the average V out, and since you have V line to line peak, you convert this one to peak. This is line to line. Means you have to multiply. This is VRMS multiplied by root of 2 to make it peak. And divide by pi. Okay, and this, times cosine alpha. You have this term. You have information about this. So you can be able to find your alpha needed to supply this much current. So that's the first requirement here. After that, you have to simulate this. You have to get your components in Simulink, connect this circuit, and here now, and this is another important information here. So each thyristor will be having its own pulse generator. Okay. Now, talking about this pulse generator, please keep in mind one thing, that once you use a pulse generator in MATLAB in Simulink, it will ask you for 4 information. 2 of them will be kept as default value, and the other 2 will be changed. The ones to be changed are, the period. Okay, so we have to enter your period here. After that, this is a duty cycle. Duty cycle is given. It's given 5%. We're not working in DC to DC converter, so we keep this one as it is with the default value. The amplitude will be, I think, 1, so we keep it 1. And the last information to be changed is the the time for the conduction time, or when to fire, when to start that your pulse here. So this one it depends on 30 degree plus your alpha, and this is for the first thyristor. The second one, if you remember in our explanation here, the second one should be 90 plus alpha, okay, for T2 and so on. So according to this chart here, you can know when to fire T3, T4, and 5 plus your alpha. Of course, the alpha calculated from here. Okay. Now the last information, which is this alpha here, or this time, it's requested in seconds, not in degree. But your time is the one you have. It's in degree. So how we can convert that one? The conversion is it's really simple. For the period, which is 1/50 for our case hertz, that is 0.02 seconds. So this will last for 360 degree. Okay, the whole, if we start from 0, 90, 180 to 70, and we come back to 360. That's the cycle. This is the cycle, the period from here to here. Now, for each delta we have, let's say, for example, alpha equals 60, the one we calculated here. So T3, or let's say, let's say, for example, 35 degree, our alpha. So 35 plus 30 would be 65 degrees. So at 65, we have to fire T1, sorry. So now to cover this one, we do this cross multiplication, and you'll find that X, okay, in seconds, will be all the time. Now this 0.02 divided by 360 and multiply by our alpha here, the one we need to convert. Not alpha, but 30 plus alpha. For our case is 65 degree. Okay, to generalize our formula, you can say that for any given alpha or any given theta, let's say, which is alpha plus x, to convert this one to seconds, we have just to do one thing, which is one constant, 1 over our frequency, which is this one, t, times 360. So this will be all the time constant. Of course, if you don't change the value of our frequency, if you keep it all the time 50, if another exercise gives like 60, this should be changed to 60. But if for our case, it will be all the time constant, this part here, multiply by, okay, the x, the one we need to convert, 65, multiply by 125, if we add 90 to 35 here, 125, and so on. So this is the value. Once you do this multiplication here, or this calculation here, it's the value you have to enter here, not in degree. One more time, not degree. Okay, but in seconds. And this how you can change everything, convert it from degree to seconds. You have to use this formula here. So and you do block by block, or you should have like 6 of those pulse generators connected to each thyristor. Now, once it's done, you have to simulate. You have to plot the 3-phase. Let's say you can do like line to line if you like, or only phase, up to you, along with this V out in the same graph. So this graph here plus V out. Okay, I think should come something like this. Okay. So from here to here will be 1, 2, 3, 4, should be 6 pulses. Okay, and after that, you select one of the phases to plot the current coming from that phase. You can select A, B, or C, any one of them. Usually we select the reference one, this one, because this one has 0 degree as phase shift. This is 120, 240, or minus 120. Okay, so we select the first one and we plot IS for that source. The load will be the current coming here across this load also, and the voltage and current across the thyristor. Sorry. Now, the thyristor itself, the block of the thyristor in Simulink, it has 3 inputs, or 3 terminals, sorry. And there is one extra terminal here, which is M. This is for measurement. If you connect this one through max multiplexer, this will give you, we'll take this one, convert it to bus, because it will collect all information about this thyristor here in terms of current, voltage, and whatever it has as information, and you will be able to see it here. You connect your oscilloscope, and here also you can select, once you double click on this max here, after simulation, after the first simulation, you double click on it, you can see all presented or present information from this thyristor, and you can select one by one, or 1 or 2, or now the number of signals that you need to display in your oscilloscope.